foundational concepts in heat transfer. So we're talking about the key ideas and tools that chemical engineers use to figure out how fast energy moves when there's a temperature difference. And, getting this right is absolutely crucial for designing pretty much any industrial system out there. Okay, to really get into it, we have to start with the three main ways heat actually moves around. First up, there's conduction. That's just heat traveling through something that's not moving, like the glass in a window. Then you've got convection, which is heat moving between a surface and a fluid. Think blowing on your hot coffee to cool it down. And finally, radiation. This one's pretty cool. It's energy that travels as electromagnetic waves and doesn't even need a medium. Like how the sun warms you up? So once we know how heat moves, how do we calculate it? Well, for our second point, each of those modes has its own guiding equation. Conduction is governed by Fourier's law. For convection, we use Newton's law of cooling. And for radiation, that follows the Stefan-Boltzmann law. All right, so how do engineers apply all this in the real world? Finally, when it comes to things like heat exchangers, there are two main methods. You've got the log mean temperature difference method, or LMTD. That's your go-to for figuring out the size of a new exchanger when you already know all the temperatures. The other one is the effectiveness NTU method. This is what you'd use to predict how an existing exchanger is going to perform, especially if you don't know those outlet temps. Let's dive into more detail.
Have you ever felt that biting chill in the air or the amazing warmth of the sun on your face? Well, what you're feeling is energy on the move. And today, we are going to decode that invisible flow. We're talking about the science of heat transfer. It's a great question, right? Think about it. That pot handle gets hot because you're touching it, or at least it's touching the hot pot. But the oven, that's warming you from a distance, through what seems like totally empty space. So how on earth does that work? Well, the answer lies in what I like to call the 3 secret languages that heat uses to travel. And to decode them, we're going to step into the perfect laboratory for this, a busy kitchen. So here's our game plan. We're going to start with the basics, then we'll break down the 3 main ways heat moves. That's conduction, convection, and radiation. And finally, we'll see how all this science gets put to work in the real world. Let's dive in. First things first, what are we even talking about when we say heat transfer? What does it actually mean? You might have heard of thermodynamics, which often looks at systems when they're all balanced out. Heat transfer, it's all about the action. It's the science of how fast energy moves from a hot place to a cold place. The key word here, the thing that really matters, is the rate of that flow.
All right, let's get into our first mode of transfer, conduction. And you can think of this one pretty simply. It's basically heat by touch.
So this is heat transfer happening at a molecular level. Imagine you've lined up a bunch of dominoes. You just push the first one and boom, that energy gets passed all the way down the line. But the dominoes themselves don't actually go anywhere, right? That's conduction. It's just energy moving through direct molecule-to-molecule interaction. And here's how that works in real life. Picture this. The heat from inside your house gets the molecules on the inner surface of a brick wall all energized and vibrating. They start bumping into their neighbors, who bump into their neighbors, passing that energy right through the solid wall until you can feel it on the cold side. Now, the science behind this is all wrapped up in something called Fourier's law. Basically, it just tells us that the rate of heat flow depends on the area, the temperature difference, and this really key property of the material called thermal conductivity, or K. You can think of K like this. Materials with a high K, like copper, are like a superhighway for heat, and those with a low K are like a roadblock. They're insulators. Okay, next up is our second mode, convection, and this is where the stuff carrying the heat actually starts to move around. So unlike conduction, where everything stays put, convection absolutely requires a fluid, like air or water, to be in motion. The fluid literally picks up heat from a surface and physically carries it somewhere else. It's a delivery service for heat. And this fluid movement happens in 2 main ways. First, you've got forced convection. That's when something like a fan or a pump is physically pushing the fluid around. But then there's natural convection, which is what happens when temperature differences cause the hotter, less dense fluid to rise all on its own, just like how a radiator heats up a room. Here is a perfect, everyday example. We all do this, right? You blow on your hot coffee. What you're actually doing is using forced convection. You are forcing air to move over the surface, and that dramatically increases the rate of heat transfer, carrying the heat away way, way faster. The math behind this is called Newton's law of cooling. Now, the key variable here is H, the convection coefficient. And unlike thermal conductivity, H isn't just a simple property of the material. Oh no. It depends heavily on how the fluid is moving, its speed, if it's turbulent. It's a much more dynamic and honestly trickier value.
And finally, we get to the most unique mode of all, radiation. This is the one that's a true rebel. It's heat that needs no medium at all to travel.
Yeah, this is the one that just breaks all the rules. See, conduction and convection both need something to travel through, a solid, a liquid, or a gas. Radiation? Nope. It couldn't care less. It sends energy out as electromagnetic waves, and those waves can travel through the total, complete emptiness of a vacuum. And there is no better example of this than our very own sun. It sends warmth across 93 million miles of empty space to reach us here on Earth. And that entire, incredible journey is powered by one thing: radiation. Now, the science here is just, well, it's striking. The equation that governs this shows that the energy being radiated is proportional to the temperature raised to the fourth power. Let me say that again, the fourth power. This means if you just double an object's temperature, it radiates 16 times more energy. It's not a gradual increase, it's an absolutely massive jump.
So let's do a super quick recap. You've got conduction, which is heat transfer through molecular touch. You've got convection, which is heat carried by a moving fluid. And you've got radiation, which is heat traveling as electromagnetic waves. 3 totally distinct ways for one fundamental process to happen.
So let's go back to our kitchen. That burner heating the bottom of the pan, that's pure conduction. The steam rising up from boiling water, that is convection in action. And that warmth you feel on your face when you stand near the oven door, that's radiation. And in the real world, all 3 are very often happening all at once.
Okay, so now that we've decoded these 3 languages of heat, let's take a look at how engineers actually use them to solve real-world problems.
Well, a classic challenge in engineering is designing something called a heat exchanger. It's just a device that transfers heat between 2 fluids without letting them mix. But how do you figure out the right size or predict how well it's going to perform? Well, engineers basically have 2 main tools they can use for the job.
And the choice between them really depends on your goal. Are you designing a brand new system from the ground up? Then you'd use one method to figure out exactly how big to build it. But what if you already have a system and you just want to predict how it's going to perform under new conditions? Well, then you'd use a different method. It's all about choosing the right tool for the job you're trying to do.
And here is a fantastic way to think about it. The first method, LMTD, is like a recipe. You already know the final dish you want to make, and the recipe tells you exactly what size pan you need to use. The other method, NTU, is more like a machine that has a known efficiency rating. You put your materials in, and you use that rating to predict what's going to come out the other side. When you think about it, from designing more efficient power plants to creating better insulation for our homes, and even developing advanced solar energy, understanding this invisible flow of energy is absolutely critical. It really leaves us with a big question. What future breakthroughs are just waiting to be unlocked, hidden within these fundamental languages of heat?